Hello everyone and welcome to the ME 296 lecture on power and alternating current. Today we're going to talk about power and finding power, alternating current, as well as special properties of power that happen when current is alternating. So first, power. Power is the rate of work done, which has units of watts, or base units of kilograms meters squared over seconds cubed, which is newtons per second. So in circuits, we don't normally use newtons to describe our circuit's behaviors, so we need to develop an alternative using values that is simple for us to find and works consistently within circuitry itself. So first of all, we know that it's a rate, so our equivalent is going to need to include a 1 over time because a rate is something that happens over time. So we must have a rate of 1 over t factor in our equivalent equation. And we also know that something has to be doing work, or work needs to be done to that thing. And in circuits, the only thing that's really moving are electrons. Everything else is standing still, so it can't be doing any work. So we need to include our charge Q, which is measured in coulombs. And we also need to have something providing energy to our system. And in circuits, that's voltage. So we've got 3 factors now. We've got a rate value, 1 over t. We've got something doing work, Q, and we've got something providing energy, voltage. So we put that all together, we get power is equal to voltage times our charge over time, which is nice and helpful because now we're into circuitry related things, but it's not super easy to count our electrons to get that Q value. And often we care only about the steady state value, so over what individual time is actually doing, not super important to us. But luckily we can substitute both of those values out because we know that current is charge over time. Right? It has the same units of Q over T, so we can substitute current, which gives us a final equation value of power is equal to V times I. Now, sometimes it's going to be simpler to calculate the voltage, and sometimes it's going to be simpler to calculate the current or to find the current or to find the voltage. So we can use Ohm's law to substitute out the value that we're having trouble calculating or that's not relevant to us right now. So if you only care about the power as it relates to voltage, you can use Ohm's law, V equals IR, substitute I equal to VR for I, and you get V squared over R, and now you have power where current is not directly calculated. And you can do the other way too, where you wind up with I squared times R, because V times I, substitute I times R again, I squared times R. Right, so how does this go in circuits? There are 2 important parts to keep in mind. There is passive and active power in circuits. Most components that we are familiar with and going to be using are passive components, such as resistors or capacitors. And in these components, work is being done to them by electrons as they flow across them or into them. In other devices, the devices themselves are doing work on the electrons. An example of this would be a windmill generator. The wind hits the blades of the windmill, it spins, and the magnets in the core of the windmill, when they're moving, they generate an electric field which causes the electrons to move about. So work is being done to the electrons. So another good way to think about it is if the device heats up when the current's on, that's emitting power, so it's a passive component because work is being done to the device in the form of heating it up. And it's important to keep track of power because it's going to determine the capabilities of our circuit. For example, if we're powering a radio tower with only a AA battery, our range is not going to be very far. And if we're trying to lift something off of the ground using an electric motor, we have to make sure that there is enough power provided so that it can actually cause the object to move over time. Right, so that's the basics of power, and we're going to come back to that a bit later after we cover some alternating current. So alternating current is current that is continuously changing in value over time and will periodically reverse direction. The most common form of alternating current is a sinusoidal wave, which is generated by the wave equation shown on screen in the blue box. In the wave shown, the phase shift phi is 0, the wave shown on the plot. However, it's important to keep in mind that we're not always going to be dealing with a 0 phase shift, and that often we're going to be calculating it explicitly. So keep in mind that you may have to dust off some trigonometric expressions in order to keep track and simplify some of these equations. So overall, there are two important properties we need to keep track of when it comes to alternating current: the amplitude and the frequency. So the amplitude is commonly called V peak in circuitry, which is from the neutral point, in this case 0, to the absolute max value that it can take, so V peak. Sometimes people refer to V peak to peak, which is a different way of saying the same information, because V peak to peak goes from absolute max to absolute min, which, assuming our wave is nice and steady over time, is going to be just double the peak. So if someone says V peak to peak, then just know that that's twice V peak, or if you prefer to use peak to peak in your own thoughts, then V peak is half what you normally are thinking of. Right? I'll typically be giving equations in terms of V peak, so make sure you keep that factor of a half in mind if you use a different kind. And then frequency. So because we are dealing with physical massy systems, inertia and acceleration play an important part sometimes. So when we apply voltage, the electrons take time to start moving. They get the signal as fast as they can, but the actual buildup of movement speed to their full velocity allowed by the voltage takes a little bit of time because they have mass, and massy objects need time to accelerate. So if our applied frequency is very, very high, sometimes the electron won't have time to accelerate all the way to its maximum speed before the wave is already slowing down and reversing direction. And this can affect some values of some components we're going to be using, especially inductors. Right. We're going to cover inductors and capacitors and how they react to alternating current and whether they prefer really fast current or really slow current. We're going to cover that in the next video after this one. Right, so that was the basics of alternating current. We're going to now go back to power. So how do we calculate the power delivered by alternating current? For a simple sine wave, half the time the voltage is positive and half the time the voltage is negative. So we can't just average that over time. It's going to come out with 0. And remember that power is the work done over time. But we know that this cannot be 0 in a circuit, or else our resistor would never get hot if it was a net 0. So the solution to this is to use the VRMS value of our alternating current or alternating voltage. As an aside, I'll tend to use AC as call alternating current and alternating voltage and kind of interchangeably because they both result in the same thing. Anyway, back to VRMS. It's where we take the root mean square of our time integral of the sine wave we're doing, shown in the blue box. So because it's a sine wave, it turns out that the time average is just 1 over the square root of 2, it turns out. And now we can use this for any form of our wave, not just sine waves or cosine waves. And we can do this because of superposition and linearity of waves. And also, it's been proven, and we're going to go over this ourselves in the Fourier transform. So Jean-Baptiste Joseph Fourier in the late 1700s posited that any periodic function, any function of any shape, could be factored into an infinite sum of sines and cosines. We'll go over this in detail in an upcoming video, but the core of the Fourier series that means that any signal, a square wave, a sawtooth wave, irregular signal, as long as it's periodic in some form, we can represent it by something made out of additions of sines and cosines. And if everything is made out of sines and cosines anyway, then the RMS value is appropriate for each of those subparts, right? So that value applies to the created final wave as well. Right? So we use VRMS as V peak over the square root of 2 for every shape of wave. So we also sometimes will have a DC offset, which is just a straight line DC plus the sine wave. but we're going to calculate those separately, and then you add the DC and AC parts together at the end. Other than that, it's very simple. You just add them together. So the alternating nature does have some real-world implications that need to be dealt with depending on what circuit we're dealing with. So just like power can be broken down into passive and active, AC power can be broken down into two types, real and reactive. And real power is power that results in a net transfer of energy to our circuit, and reactive power does not result in a net transfer of power into the circuit. So the analytical difference, just equation-wise, comes from the phase shift between the applied current and the voltage response of a component, which we will go into in a great depth in the capacitor and inductor video. If you take the apparent power, which is the sum of both the real and reactive power, similar to the triangular law where you have C squared equals A squared plus B squared. You get the apparent power by taking the square root of the square of real plus the square of the reactive power. And then you can break this down into angles as well, just like in trigonometry, and use just the apparent power times the sine of the phase shift between, or the angle between the two values. So the reactive power, one that you can think of, is an energy that is stored temporarily within a component, like how a capacitor stores its energy in an electric field. If you suddenly turn off the applied voltage to the capacitor, the electric field doesn't turn off instantaneously. It still has an effect on the circuit that's going to be still there, even afterwards. Same thing with an inductor. So a little more depth on the analysis. So it's most useful to us to analyze power as a combination of vectors. We usually place real power on the x-axis and reactive power on the y-axis, which leads us to something called phasor analysis, which describes the steady-state response of AC circuits. So phasor analysis is predicated on Euler's formula, as seen at the bottom of the screen, which allows us to treat sinusoids as a set of complex exponentials, which greatly simplifies analysis. It is so much simpler to keep track of and take derivatives and integrals of complex exponentials than to keep track of a whole sum of sines and cosines all around. So when treating power as a complex number, reactive power is designated the imaginary power and real power the real power. So this doesn't mean that reactive power is not real, just that it's convenient to treat it like a mathematically imaginary construct, especially since Euler's formula already takes into account complex numbers. So there's a whole branch of mathematics ready-made to treat reactive power as if it was imaginary, even though there are real effects that come from it. So there are several different methods of notation to indicate the phase shift and apparent power of a circuit. So the most familiar and most cumbersome is the complex rectangular form, which I will rarely use, which is a magnitude in front of a sum of the real part, which has got a cosine, plus the imaginary part, which is j times the sine. There's also the exponential form, which is what Euler's formula provides, which is the amplitude times e to the negative imaginary stuff, plus a phase shift. And what's very common, especially in engineering fields, is the polar form. And the polar form is the magnitude of our complex number and then the angle between our real and reactive power. All three of these give the same information. Some of them are cleaner to look at, some of them are easier to analyze. They all give the same information. Okay. And I will normally use the complex exponential form just because I have a background in physics, but I will try to use the polar form as much as possible in case you are all more familiar with reading engineering papers where they use the polar form pretty frequently. But be aware that you should be able to use all three forms of notation, like on a test or a homework. Okay. So that's it for right now. I will be doing a set of examples after on power and alternating current after I post the video for capacitors and inductors, and hopefully this will make a little bit more sense seeing it applied in practice. It's basically just to reintroduce you to some concepts and maybe a little bit more depthful approach to some of how we express power in AC circuits than you would have gotten in 196. All right. So coming up soon is going to be capacitors and inductors, and we'll get into exactly where phase shift comes from and its physical purpose and reason. All right, but that's all for now. Thank you for listening.